But before I do that, let me talk a little bit about what happens when I want more than 2 inputs. Suppose I have nothing but 2 input gates in the stockroom. Can I go off and build, a 4-input gate? I have 2 input ANDs. How can I build a 4-input AND? Okay, well, this is, again, is not terribly complicated. None of this is rocket science. I always wished I was an aero-astro, because then I could actually talk about rocket science, and everybody would be impressed. But I'm an EE, so I do these stupid gate tricks. And so the idea, suppose I want an XOR of many things, an XOR of n input signals. Well, one thing I notice is that I can sort of use the associativity. So if I want, A XOR B, so XOR is the plus with a circle in it, XOR C, I can do this as A XOR B, and then take the output of that gate, that 2-input gate, and XOR the output of that first gate with the second gate, and I end up with this long chain of gates, like so. And in fact, this does produce, this is a parity calculation, or if you want some modulo 2, of a bunch of signals, this big chain of XOR gates. What's the TPD of that circuit? As the number of inputs grows, as n gets bigger and bigger and bigger, how does the propagation delay of this n-input XOR gate grow? Yeah. Well, or linearly. In other words, if I doubled the number of inputs, I would essentially double the propagation delay, right? Because this chain just gets longer. Every time I add an input, I add one more to the chain. So the chain is roughly as long as the number of inputs. As the gentleman pointed out, I mean, there's sort of a -1 in there because the first gate took care of 2 inputs, but all the rest of the gates only take care of 1. Can we compute XOR faster? It's on the next slide, but just think for a moment. What's another way of organizing these things? Okay, so if I had A XOR B, XOR C, XOR D, you could say, well, I could keep doing this and just sort of build it up one at a time. But I could also sort of do them in pairs and build a tree. Okay, so here's a picture. Everybody remember that Joyce Kilmer poem? I think that I shall never see something as lovely as a tree. So you can see it's made a big impression on me. But of course, now it's irrevocably coupled in my mind to this particular slide. An EE's view of the universe is sort of strange, I guess. And you can see what we're going to do is that for each layer of the tree, we're doubling the number of inputs that the circuit can handle. Because each time we add a layer to the tree, for every input at the previous end leaves of the tree, when I add a new layer, for each input, I'm basically doubling the number of inputs that I can accommodate at the next layer. So the number of inputs is growing exponentially as I make the tree deeper and deeper. Alternatively, if I want to think about if I have a certain number of inputs, how many layers of tree do I need? What do I need to do? Yes? Log base 2 of n. So in fact, the TPD of this tree sort of grows as log n. And in general, with 2 input gates, or if it was 3 input gates, it would be log base 3 of n. If it was 7 input gates, it would be log base 7 of n. But there's a sort of logarithmic argument that I can make. Okay, once you tell me how many inputs I'm allowed to do in a single gate, I get this sort of logarithmic effect. So if I want to build a function that looks at all of its inputs, I can't usually do better than a log n TPD. Okay, and the details of the constants of, is it 2 times log n or 3 times log n? So that depends on the details of the complexity of each of the gates here. Okay, can I take, if I want to do the NAND of 57 guys, can I build a tree of NAND gates? Would that work? You can sort of see I can do it with XOR. Now I'm asking the question, suppose I want a 57 input NAND gate. Could I just build a tree of NANDs? No. I agree with no. So explain why no.
I guess I'm just thinking about the idea of a 57 NAND gate would have 1, 0, and then a very large amount of
The pesky thing, so you're sort of you're zeroing, zooming around sort of what I think of as the right thing. It's the inversion that's getting in the way, right? I can build a tree of AND gates and a tree of OR gates. Positive logic, trees up very nicely. This inverting logic, because each gate inverts. Now I'm stuck on the next layer dealing with inversions. And so what happens is the trees get a little bit more complicated to build. If I wanted to build a 57 input NAND gate, maybe what I would do is to build a tree of ANDs and then just put the inversion at the end, and I can build the tree. So thinking about how to do a tree implementation, okay, to get that logarithmic TPD of inverting logic functions, it takes a little bit of thought. And there's different ways to think about it. And in fact, when you get around to designing your beta, which is our 32-bit computer, we're going to need a 32-input NOR gate to do one of the functions that we want to do. And you're going to have to think a little bit about how best to do that. Okay, are trees always best? I mean, we've talked about this trees as somehow having really satisfactory sort of asymptotic behavior. In other words, as the number of inputs grows very large, trees seem to be the best we can do. And the answer is, well, not particularly. We can imagine a different implementation, which is a lot more compact in some ways. Here's a wide fanned-in OR gate. So we can see that what we have here is a resistor pull-up. So if none of these pull-downs is on, then this intermediate node here will be 1 because of the current through the resistor, and then I'll get a 0 out. Okay, so the question is, when do we stop basically building really wide fan-in gates with stack, either using this sort of tricky technique of getting rid of the pull-up circuit and only putting in the pull-down circuit? This is a static logic, a logic that has some static power dissipation, or just using more and more FETs. And when do we go, when do we do this, and when do we actually go just build a tree of 2-input gates? And the answer is, it's because what happens is every time I add a new input, I'm adding some capacitance, so the gate does start to slow down. This crossover tends to be right around 4 inputs. So the idea is that if you have 4 inputs or less, you just build a big gate to do it. And you have more than 4 inputs, then you start thinking about how to use trees or chains of smaller gates, smaller fan-in gates.